In this session we'll be doing quite a bit of algebra, and that will involve for you quite a bit of homework, I'm afraid. There's quite a lot of derivation in this session. Now, there's something strange about these two by two, so even-sized matrix representations that have the same commutation relations as the operators, you're dealing directly with the operators, and that is their values, the actual numbers you get for the m and the l, which is a bit unexpected. So if you look, you can't see it, but previous session, the 2 by 2 matrix representation that you got for, let's say, L squared, the L squared operator. It was, and remember this, take a mental note, it was, and I'm reading it off the board here, you can't see it, but it's 3 h bar squared over 4, so 3/4 of h bar squared, and the matrix was a diagonal matrix, 1, 1 down the diagonal, and the other two, the cross diagonal, two elements were 0, 0, so a diagonal matrix is to be expected. But concentrate on the 3/4, 3/4 h bar squared into like 1, 0, 0, 1. Now, remember from operator, when you're dealing directly with the operators, the L squared operator gave you an eigenvalue of L times L plus 1. Okay? So, what's the value of L if L times L plus 1 equals 3/4? Okay? Well, it's a half. Right? A half times a half plus 1, so that's a half times 3 over 2, that's 3 over 4, that's 3/4. So your L now is a half, and that's a big hint, we're heading towards spin. Okay. Now what about M? Well, if you remember from using directly the operators, the M eigenvalue, remember M was the component of the eigenvalue of the Z component of the angular momentum along the Z axis, and it was it took values ranging between minus L and L. Okay. Well, if L is a half, that means that M ranges between minus a half and a half. Right? It jumps. You know, M's integer. Well, M jumps by 1 increments of 1. So it goes from minus a half to half. So your L is a half, and your M is plus or minus a half. Right? That's interesting. Different from you know, what we were getting before. Now these matrices are so simple. They're only 2 by 2 matrices. You know, the simplest case. So as homework, I ask you to actually calculate what those matrices are. Now towards the end of the previous session, I just threw them at you. I just gave them to you. But to see if you can actually calculate them, what they should be, by using the commutation relations between, like, you know, Lx and Ly, or Ly and Lz, or Lz and Lx, and L squared and Lx. That commutator should be 0, and L squared and Ly also 0, and L squared and Lz also 0. But by using all these commutation relations, you should be able to create a whole string of restrictions, constraints, on the values of the 4 elements of each of these matrices. So if you say you're trying to find the 2 by 2 matrix representation of the LZ operator. So let the matrix be A, B, C, D, the 4 elements. Now this matrix has to be Hermitian, Okay, so you got, now that's true of all of them. So there you got a bunch of constraints. So you know, take it as an intellectual challenge, as a homework, by using the commutation relations and the fact that these matrices have to be Hermitian, because you know, the operators themselves are Hermitian, so the matrices must also be Hermitian. Remember, a Hermitian matrix means, so if you have a Hermitian matrix M, if you conjugate it, you change all the i's to minus i's, and transpose it, so let's see here, so the rows become the columns, and the columns become the rows, and transpose it, you'll get the same M. Okay, so M equals M conjugate transpose. So apply all those constraints and the commutation relations, and see if you can derive the 2x2 matrix representations for Lx, Ly, Lz, and L squared. Okay, yeah, try that. So that's what's said here, and ask you to do that for homework. Right? All this you know, this active stuff. If you bite the bullet and actually do this, so it's a great learning experience. Also, I'm assuming most of you are alphas, and so being alphas, you know, by definition, in the top percentile of intelligence, you're smart. So I'm hoping you will, you know, because of your brain power, you will be self-motivated, and you just like learning because you like learning, right? You don't have to be pushed. You just take the challenge and run with it. So you know, here's an interesting challenge. See if you can actually derive these 2x2 matrix representations of Lx, Ly, Lz, and L squared. Okay. Right. Now there's another way you can do that, and it's via what's called the eigenvalue spectrum. Now, spectrum, what does that mean in this sense? In this context, it just means all possible eigenvalues. Right? That's all it is. You probably heard the expression in English, oh, the whole spectrum, you know, meaning all possible ways of something. Right? So in this context, the eigenvalue spectrum, it just means all possible eigenvalues. And this alternative way is sort of similar to what we were doing for the simple harmonic oscillator problem before, where we had step-up operators and step-down operators. So what we'll do now is very similar. We will apply step-up operators on eigenfunctions, and that stepped up eigenfunction will have an eigenvalue that's increased compared to what the eigenfunction normally has. You know, the eigenfunction's normal eigenvalue. All right. So we'll define now these. Don't be confused. I put a hat here. I could almost not put a hat, or I could put an M or something. These operators here now are matrix. They're matrices, right? They're matrix representations of the differential operators, if you like. So don't be confused by these hats. These are not the old hats of differential operators. These are now matrices. Okay. But we don't know what they are yet. That's the whole point of the exercise, right? We're going to find what they are from their eigenvalues. So we're going to calculate for their eigenvalues. But we do assume that these matrices, these matrix representations, obey the commutation relations. Right? If they're going to act as representations, you know, behaving in equivalent manner as the ordinary operators, the differential operators, then they have to obey the same kind, you know, the equivalent set of commutation relations, right? and be Hermitian matrices and so forth. All right. Well, here, if if these hats here were the old differential operators, then you had these. I've written them out again. Well, we've got 6 relations. These 3 non-commuting relationships, the commutators, right? And these 3